What would you do if you were able to tell what's gonna happen in 1 week? Well, given that the name of my project at the university is Detection and Identification of Pathogens on Apple Trees using hyperspectral imaging and AI, my answer would be looking at apple trees to see if they will fall sick in a week. But this isn't sci-fi no more. You see, with hyperspectral imaging and AI, we are already able to look into the future of a plant or a tree and see if it's gonna experience a pathogen outbreak in a few days based on the frequency of light it reflects. Now, how does this work? Every element, from hydrogen to oganesson, reflects a different spectrum of light. Hence, every material reflects a different spectrum of light. Using hyperspectral imaging, you can, for example, differentiate between a normal leaf and a perfect replica made from paper, and all you need is a mere photo. Or you can recognize what parts of a leaf have pathogens on them and tell the pathogens apart. And they don't even have to be visible to the naked eye yet. So these are some pictures that I already took within the project. Here is a normal RGB photo that you get from most every camera, which obviously consists of red, green and blue wavelengths. And here is a hyperspectral cube. Since hyperspectral images have a lot more wavelengths than just RGB, if you were to stack them on top of each other, you would get such a cube. And now comes the AI part of the project. If you would like to actually use the hyperspectral cube and see what's inside, you technically could go frame by frame through the wavelengths, but that doesn't make much sense. So what I'm doing instead is open a program and let it digest the hyperspectral cube for me. The goal is to automate this process, because even though I have the AI program, I still have to manually categorize the visibly deficient parts of the leaves for it to work properly. And as already said, we just wanna look at a tree and immediately see if there are any invisible incubating pathogens. Unfortunately, the real world usage is still pretty far in the future, as I can demonstrate on this photo. I took it in close to perfect conditions in a lab, selected all the different parts like stem, healthy tissue, lesion, etc. And this one whole leaf, which was healthy for the most part, got diagnosed by the AI algorithm with early chlorosis from head to toe because its color differed from the other two leaves by a few shades. Now imagine if you would try to use this technique in a real apple orchard. The footage would be straight up unusable for the AI program. But I can show you that the different parts of the leaves really reflect different spectra, and you can tell them apart just based on this spectral signature, so to say. For example, you can see that the curve of the lesion looks unlike any other on there. So since you already know what the project is about, let's look at why it's so important, and then I'll show you what the hyperspectral cameras look like. One of the main diseases that we are now focused on is apple scab. It's a hardy disease that can come back year after year into your orchard, and when it does, the farmer has a bad year. Apple scab is a fungal disease, and the symptoms are big black spots on the fruits. I'm sure you've already seen it. The problem is that when a farmer has such apples with black spots, the spots aren't going anywhere, and the farmer can't sell these apples on the fresh market anymore, which means he has to sell them way cheaper, which means he can go bankrupt. And no farmer wants that. The goal of hyperspectral imaging in this case would be to detect the apple scab in a still treatable stage before it forms the black spots and save the farmer a bunch of money. And there are three main types of hyperspectral sensors. First is the whisk broom, second the push broom, and third the snapshot type. For most use cases, you would probably want to use the push broom, since it's relatively fast and has a good resolution. It only scans one line at a time, so you either have to move the camera in one direction or move the object in the other. But the results, at least in laboratory conditions, are good. Then we have the snapshot type. This takes a quick snapshot of all the different wavelengths of the object and does it fast, but the resolution isn't that good. And the whisk broom. This hyperspectral camera scans one single pixel at a time. It works kind of like a 3D printer. The upside is a great resolution of the image, but it simply takes way too long. And this whole comparison is why I'm using the push broom camera for this project. So this was the introduction of my university project, and thank you for watching.